Timeless Concepts from Physics Helpline. This is a video tutorial series through which we will sharpen our problem solving skill. First, we will analyze the problem on hand to find the related concepts. Then using these, we will develop a method which will produce the solution. This will help the students aspiring to get into IIT to understand the much needed advanced theories and applications in physics. In this video tutorial, we will discuss a multiple choice question with only one correct option about thermal conduction through two identical metallic rods connected in series and parallel. The question is as follows. An experiment on thermal conduction was performed using two identical rods, each of length L, area of cross-section A, and coefficient of thermal conductivity K. They were first connected one after the other in series between two vessels, one containing water at 100 degrees C and the other containing ice at 0 degrees C. The experiment was repeated by placing one rod on top of the other in parallel. If Q1 and Q2 be rates of melting of ice in grams per second in the two cases, then the ratio Q1 by Q2 is. The options are 1, 1 by 2, 1 by 4 and 1 by 8. Before proceeding to solve the problem, let us recall the related concepts. Heat energy is conducted through a metallic rod of length L and area of cross-section A according to the equation dq by dt is equal to minus Ka into d theta by dx, where dq by dt is the rate of flow of heat along the rod, K is the coefficient of thermal conductivity of the material of the rod, and d theta by dx is the constant temperature gradient along the rod. Let the ends of the rod maintained at temperatures theta 1 and theta 2 such that theta 1 is greater than theta 2. Then d theta by dx is equal to theta 2 minus theta 1 divided by L, which is equal to minus theta 1 minus theta 2 by L. Therefore, we have dq by dt is equal to Ka theta 1 minus theta 2 by L. Now, let us consider melting of ice. Heat required to melt 1 gram of ice is equal to its latent heat L. Therefore, heat required to melt dm grams of ice is equal to L into dm. If dm grams of ice melts in time dt, then heat absorbed per second is dq by dt is equal to L into dm by dt. Therefore, rate of melting of ice Q is equal to dm by dt, which is equal to 1 by L into dq by dt. Since L is a constant, we have Q varies as dq by dt. Now, let us understand the similarities between thermal and electrical conduction. Heat flows along a metallic rod due to a temperature difference theta 1 minus theta 2 across its ends. Similarly, electric current flows along a conductor due to a potential difference V1 minus V2 across its ends. Now, dq by dt is equal to Ka into theta 1 minus theta 2 divided by L. We can put it as equal to theta 1 minus theta 2 divided by R by defining thermal resistance R is equal to L divided by Ka. Similarly, electric current I is equal to V1 minus V2 divided by R such that electrical resistance R is equal to rho L by A, where rho is the resistivity of the metal. Now, rho is equal to 1 by sigma, where sigma is its conductivity. Therefore, we write R is equal to L divided by sigma into A. When two conductors of resistances R1 and R2 are connected in series, then the effective resistance is Rs is equal to R1 plus R2, and when they are connected in parallel, the effective resistance is 1 by Rp is equal to 1 by R1 plus 1 by R2. These expressions are valid for both thermal and electrical resistances. Now we are in a position to solve the problem in the question using these concepts. We can solve it by using two methods. Method 1. It is the direct method using the fundamental concept of conduction. We start with the equation dq by dt is equal to Ka into theta 1 minus theta 2 divided by L. For a rod of length L, area of cross section A, and coefficient of thermal conductivity K. When two such rods are connected in series, length becomes 2L, but A and K remains unchanged. Therefore, rate of heat flow in this case is dq1 by dt is equal to Ka into theta 1 minus theta 2 divided by 2L. And when they are connected in parallel, area of cross section becomes 2A, but L and K remain unchanged. Therefore, rate of heat flow in this case is dq2 divided by dt is equal to K into 2A into theta 1 minus theta 2 divided by L. Dividing, we get dq1 by dt divided by dq2 by dt is equal to 1 by 4. Now, from equation 1, we have rate of melting of ice dm by dt is equal to q, which varies as dq by dt. Therefore, q1 by q2 is equal to dq1 by dt divided by dq2 by dt, which is equal to 1 by 4. Therefore, the correct option is C. Method 2. In this method, we will use the concept of thermal resistance. We have dq by dt is equal to theta 1 minus theta 2 divided by R, where thermal resistance R is equal to L divided by Ka. We observe that dq by dt varies as 1 by R and Q varies as dq by dt. Therefore, we have Q varies as 1 by R. In the first case, we have R and R in series. Therefore, Rs is equal to R plus R, which is equal to 2R. And in the second case, we have R and R in parallel. Therefore, Rp is equal to R by 2. Now, Q varies as 1 by R. This implies Q1 by Q2 is equal to Rp by Rs, which is equal to 1 by 4. Therefore, the correct option is C. This completes the answer to the question.